Hi, I'm Vassilis Lyberatos, and I'm going to present you our work entitled Perceptual Musical Features for Interpretable Audio Tagging. Our work is an application of XAI methods in music audio tagging. We perceive interpretability as the ability to explain and understand of how a machine learning model works. A simple taxonomy of XAI methods is given by Guidotti, is the black box explanation methods and the transparent box design methods. Music audio tagging is a task of music information retrieval community, and the purpose is to classify music tracks based on various attributes. Some examples are that we can classify music tracks based on emotion, genre, or instrument. Our motivation is to tackle problems such as label ambiguity or concept drift, and try to construct an interpretable pipeline that can categorize tracks with an explainable way. Here is our pipeline. We have our dataset. We extract with three different methodologies features from the dataset. We use symbolic knowledge, we use signal processing features, and DNN based features. Then we use these perceptual features, so-called perceptual features, as an input to our classifiers in order to obtain our labels and our explanations. The datasets we used are two. The one is the MDG Jamendo dataset for the mood tagging task, and the GTGen dataset for the gen recognition task. For the feature extraction, as I said before, we used three different methodologies: the symbolic knowledge, the deep neural networks, and the signal processing. As far as the symbolic knowledge is concerned, we obtained features by using the functional harmony ontology. These features are based on the notions of music theory and try to capture the harmonic density of the track. The second way we obtain our features is through DNNs that was trained in a dataset that was curated from musicians. An example of this feature is the dissonance, which is a feature that indicates of how noisy is our track. The architect that we used for these features is a VGG style CNN neural network, as shown in this image. The third way we obtained the perceptual features is through signal processing. We used an audio analysis tool called Essentia, and we obtained 23 signal processing features. An example of these features is the chord change rate, which indicates of how many times we have change in chords. Since we obtained our perceptual features, that are features that are human understandable, we use them as an input to an interpretable classifier called XGBoost. We chose XGBoost because it is famous for its performance and it is also kind of interpretable. Our results show that indeed we are close to state of the art, and we obtained results that are good enough. for the explainability part of our work, we used 4 different approaches to try to understand of how our models work. The first one is an ablation study, where we experimented by feeding our model with different combinations of feature groups. It is the permutation-based feature importance explanations, where we randomly change the values of features and try to measure how much our model is influenced. The third way we obtain explanations is through supply values, that are values that are based on game theory concepts. And the last way is through XGBoost built-in feature importance. That's a feature importance based on how many times the features are appeared in the trees. Here we can see the results of our ablation study. We can conclude that all features contribute positively in increasing the performance of our model. And also we can say that the signal processing features are the most important ones. Here we provide a comparison between the XGBoost built-in feature importance and the permutation-based feature importance. We can see here that both explanations are aligned, since among the four most important features we have the spectral flux, the length, and the danceability. Here we can see a comparison between explanations given through supply values and XGBoost feature importance. This is an example for predicting the label trailer of a music track. You can see here that also both methodologies are aligned, since we have length, spectral flux, onset rate, and spectral entropy as the most important features. We can say here that supply values provide more descriptive explanations, since we can see that, for example, spectral flux, when spectral flux has high values, it has a positive impact on predicting the label trailer. This example also is aligned with the common knowledge that trailer has a voice in it, and spectral flux is a feature that is used mainly for detecting voice. A second example is for predicting the label disco. Here we can see also that we have an alignment between the two different feature importance approaches, and we can see also that we have reasonable results, since disco music has loud beats, and our model here says that if we have high bit louds, this has a positive impact on predicting the label disco. To conclude, we can say that feature engineering is very important for music and audio tagging, and it is crucial to obtain features that are trustworthy, understandable, and increase the performance of our pipeline. Also, it is important to say that the domain knowledge should not be discarded, and it may be used in nice ways in order to extract useful features. In future work, we plan to use an experiment on how to use explanations to improve the performance. We would like also to have an extensive human evaluation of the explanations, and to see in what extent explanations help people to trust our models. And also we plan to introduce new features based on the notions of music theory.